Okay, I'd like to go over very quickly the difference between gravity and gravitational velocity. Okay, this is a very important distinction that you need to understand if you want to understand the concept of gravitational velocity and the time dilation that results from it. So the first example is going to be very little overly simplified, but I think I'm going to do that to make it clear, and then I'll go for a more accurate example right after. So the way to imagine gravity is a hill, okay? And let's start with a fixed hill, two fixed hills. One that is a certain slope and a certain height. And then we'll just say that the planet or the attractive force is at the bottom, but for now, just assume it's a hill. And then for gravitational velocity, we'll imagine a bigger hill that's higher, but the same slope. Okay, slope S and S1, S1 and S2, and H1 and H2. Okay, so S1 equals S2, but H1 H1 is greater than H2. Okay, so the slope of the hill is the gravity, okay? I'm just going to stick with one color at this point, okay? The slope of the hill is the gravity, and that's the acceleration you experience when you're standing on that hill, okay? Now, in this case, the slopes are the same, so two people will, on either one of these hills, will experience the same gravity or slope, okay? But if there was a big bucket of water or a fountain here, let's say a fire hose or a river. Let's just say a river is here, okay? And there's water flowing down this hill, okay? Okay, down at the person. The water, the speed of the water on the lower hill, okay, on the smaller hill, the shorter hill, will be less because it has less time to build up the speed when it hits the person. This is the gravitational velocity, okay? And so if, as I've stated and as well-known fact, the gravitational velocity or the flow of this water, and the analogy is this is space-time. These are space-time particles, let's call them, space-time quanta. The rate of flow across the person is what determines the amount of time dilation that person experiences. Okay, so in this case, even though they're both experiencing the same gravitational force or acceleration because the slope of the hill is the same, this person on the higher hill is experiencing more time dilation because the water has had a longer time to run down the hill and is moving faster across him when it hits him. So that's the gravitational velocity, and that's the difference in time dilation. Okay, so this is the simplified example. Now let's go to the more complicated but more precise example. Okay, so again, we have gravity on this side and velocity on that side. Okay, now I showed before a hill with a fixed slope. Well, gravity wells are parabolic sloped hills. So therefore they are shaped in an ever growing curve. It's actually the other direction, but I'm just going to do it this way for ease. So they get steeper with time or less steep with time. How's that? That's right, less steep with time. Now, I drew that too big, but anyways, so so that's a small hill, okay? So planet A, okay, or a certain size hill. And now for planet B, we're gonna draw a bigger hill, okay? This is a bigger hill, but it's still the same shape, okay? So it's still a parabolic curve, okay? Now, the difference is the radius of the planet determines where on the line you're going to be located. So for this planet, we have a radius of r, okay, and then let's just say for like we said, this planet is 10 times higher. Okay, it's 10 times higher. Okay, which is my example from before. Than this planet. This is so H2 H1 H2 equals 10 times H1, okay? The height, okay? Now, where you're located on the planet is where, so here, you're going to be located at the first radius of the planet, planet 1, and it's the slope at this location that determines the amount of gravity. So this is the gradient, okay, the gravity you experience, okay? But again, it's the speed at which water flowing down this hill builds up before it hits you, which determines, this is your gravitation, determines the amount of time dilation you experience, okay? Now here, so gravity is the gradient, the acceleration is the gradient, okay? Gravity, the force you experience, the strength of the force that you experience is the gradient or the slope. Derivative, it's the derivative, if you're familiar with calculus. Now here, this person, we're going to make this, he's going to be located at 3.3 R1, okay? Again, this is all about square root. You see why I manipulated it. But at this point, the slope at this point in the parabola is going to be the exact same as this point, okay? Even it's higher up, but it's bigger slope, so it all equals out. So he is also experiencing the same gravity, okay? But the water in this case, or the space-time particles, has had more time to accumulate speed. It's a longer, much higher curve, and I should have drawn this to scale, but the water here is moving much faster. So the velocity here, the gravitational velocity is much higher. So this person will experience a greater amount of time dilation than this person, even though their slope or the gravity or the acceleration they're on is exactly the same, okay? Now, a couple of other examples I did was like an orbit. So if you're orbiting, so you're above the surface, so let's say you're a satellite up here, you're not on the surface of the planet, but the water is still, or the space-time is still flowing past you, and you're still experiencing time dilation. Also, but you're not experiencing acceleration because you're orbiting around the planet, as we described before. Now the weird case here is, let's say this is a crust and not a planet, not a filled-in planet. So the area here is hollow. Down below this curve is hollow. Then here you'd be in free fall, but for some reason the water is still coming through, or the space-time is still flowing past you, or it's creating a pressure that also creates the same time dilation that you experience on the surface. So that's an interesting change to the analogy, going from water flow or gravitational velocity to gravitational pressure. The units are the same though, it's still meters per second or velocity. And of course, the other example is, now here's the strange example, and again, this is where the flow example breaks down and it becomes a pressure, the pressure analogy is better. If I'm actually falling down the hill, okay, if a person's falling down the hill, I'm experiencing all the different time dilations as I go down. So my time is dilated here, and the dilation is increasing as I fall down the hill. Now, you could argue, if the flow model was correct, you'd be falling along with the space, and therefore you wouldn't experience the time dilation, and therefore it would, if that was the case, the flow model would be verified. I don't believe that is the case, though. I do believe that as you fall, you will experience all the time dilations, even though you're flowing with the so-called gravitational velocity or the flow. So that would indicate the pressure model is more accurate. Okay, this is really a pressure, it's not a flow. And that as it falls down, you're going through the different levels of pressure, and your clock is slowing. You're not falling with the space-time flow or river model. Okay, so it's something to think about. Anyway, so hopefully this will enable you to understand the difference between gravity, which is the slope or the derivative, versus gravitational velocity, which is the speed at which space-time is coming back, flowing past you, or the pressure at which the space-time sits, even though the units are reported in meters per second squared. Thanks.